Hi, hi, everybody. Hi, good people. Today we're going to do some applications in section 3.4, and we're going to start with the adjoint of a matrix. The adjoint of a matrix is something that's useful or to find an inverse of a matrix. As you know, finding an inverse of a matrix can be a pain, and adjoints give us another way to find inverses. The first thing I want to remind you is the idea of cofactor. We learned that a cofactor is the matrix defined by -1 to the I plus j power times the determinant of the matrix obtained by deleting the ith row and the jth column. And a matrix of cofactors would be instead of having here C11, instead of having A11, A12, A1n, you have a C12, C1, C1 and da da da. So each A, every A that was here, you got rid of all the stuff, put it in whatever. That's the ratio of cofactors. I don't want to dwell on this too much. And if you transpose this matrix, so it's the same cofactors, but now you're moving them, you're transposing it, then that becomes called the adjoint. And the adjoint, now how do you find the adjoint of a matrix? Well, it's a little tedious, but it's straightforward. So start over here. So here's the top number is -1. Take the -1, knock out the row in the column. You have this little matrix here of -2, 1, 0, -2. Find the determinant. 4 multiplied by -1 squared, and pow. Now notice I never. Well, why is it +4? Shouldn't it be -1 times -1 squared times that determinant? And the answer is no, because that's what we only multiply this -1 when we're actually trying to figure out the determinant. But this here is not the whole determinant, it's just the cofactor. The cofactor is the thing I multiplied -1 by. So just be clear about that. Anyway, so you do this whole process, and this is what you get. Then you transpose it, and that's what you get. That's the adjoint. And what's cool about adjoints, it gives us a method to find an inverse of a matrix. So it turns out, here's a cool formula. If A is invertible, not every matrix is invertible, but if A is invertible, then the inverse is 1 over the determinant times the adjoint. So all I got to do is crunch out the adjoint, which is a whole bunch of determinants, granted, divided by the determinant of A, and that will give me the adjoint of A, the inverse of A, I'm sorry. I guess I'm noticing here that this is not actually a very practical method. It's a lot of steps, so it's not really used that much in industry. It's not really used that much, but it does have a theoretical interest because it's a way of getting an inverse, which is kind of cool. Here's a proof. I'm not going to go through the entire proof. In fact, I'm not going through any of this particular proof. But let's just use the adjoint to find a determinant. Okay. So here is matrix A, and we want to find A inverse. So basically what you're going to do is you're going to find the adjoint, which is 4, 6, this is what we just did in the previous problem, 4, 6, 7, 101, da, da, da. You're going to find the determinant. So the determinant, you could crunch this out and figure out that it's 3. Again, not a hard determinant to figure out. And what we're going to have now is 1 over 3 times the transpose of the cofactor matrix, which now gives us this guy right here. So this guy right here is the inverse of this matrix over here. And you should check it out by actually multiply. You should actually multiply this. I'd like everyone to multiply this matrix times that matrix, do it in both directions, just to confirm that this indeed is the inverse. I'm going to pause the video to give you a chance to do this. Or you should pause the video, I'm sorry. Okay. Now we're going to go on to a very, very cool, awesome theorem called Kramer's rule. Now I have a friend whose last name is Kramer, and he's Kramer's rule, but he meant it in a different way. Anyway, Kramer's rule gives us a method of solving systems of equations. So let's look at an example of it here. So here's an example. We have 4x minus 2y equals 10, 3x minus 5y equals 11. Notice they say x1, x2 instead of xy. That's why they do that, as I explained. If you have a equation with like variables, you know, it's easier just to number the variables, not come up with different letters. Anyways, so the determinant of the coefficients turns out to be negative 14 because it's negative 20 minus 6, and it's negative 14. And the, excuse me, right, negative 20 plus positive 6 winds up being negative 14. And so the determinant is not 0, so we're in business. We can get a solution. So what we do is we take the coefficient matrix, but in the x column, we replace it with the constants. And that's the top of the fraction. The bottom of the fraction is the coefficient matrix, which we already figured. Determinant of the coefficient matrix, which we already figured out, is negative 14. The top, if we just take this determinant, comes out to negative 28. And negative 28 divided by negative 14 is 2. Now, for the y variable, we take our coefficient matrix, but we replace the y column with the constants 10 and 11, and we actually get positive. This determinant comes out to be positive 14 divided by that same negative 14, and that's negative 1. So let's work it out. 4 times 2 is 8, minus 2 times negative 1, that's 8 plus 2, which is 10. That works. 3 times 2 is 6, minus 5 times negative 1, which is 6 plus 5, is 11. So it works. And that is a very cool and awesome thing. Now, we're going to use Kramer's rule to solve a 3x3 equation. I'm going to give you my own example of that. Here's what we'll do. Now, if you want to do a 3x3 equation, say here x plus by plus cz, which I would normally write. So they're writing a11, a12, a13. Like I say, when you have a lot of variables, you want numbers instead of letters. But anyway, here's my constants. So for example, to figure out x3, which we might call the z variable, we take the determinant. Basically, we take on the bottom, we have the determinant of the coefficients, and on the top, we have that same determinant of coefficients, but we replace the z column, or the x3 column, whichever you want to call it, with the constants rather than the. Now let's go through an example of that. So here is an example using Kramer's rule. I just want to show you just something else here. Give me 1 second here. So basically, this is just my own way of writing it with x, y's, and z's. So you have ax plus by plus cz equals r, and my screen sharing, why is it being paused? My screen sharing is being paused. Why is that? My screen share, what is that supposed to mean? Huh? What just happened? My whole video is messed up. Okay, I don't know what just happened there. Why is my screen sharing being paused? This doesn't make sense. I don't get it. Okay, now we're good. So ax plus by plus cz equals r. I don't know why that happened before, but now we're cool. Dx plus ey plus fz equals t. Gx plus hy plus jz equals w. So basically what I'm trying to say is that it works like this. So X is going to be, let me make this a little bit bigger. X is going to be, again, the bottom is the matrix of the coefficients. And the top, to find the value of X, I take the coefficient matrix as is, except I replace the X column with RTW, that's the constants. And then for Y, I take the matrix as is, but it's a G down there, it's a little sloppy. But for Y, I take the matrix as is, except I replace the Y column with RTW. And then for Z, I write the matrix, the coefficient matrix as is, except I replace the Z column with RTW, which is, and RTW, don't forget, was the RTW was the constants. By the way, as a separate thing, I'm not going to work at the steps here, but this would be a nice problem here. 7x minus 2y plus 7z equals 12. 5x plus 13y minus 6z equals 12. Negative 4x plus 11y plus 3z equals 10. That'll be nice for you to work out, to practice Kramer's rule. Do it this way. And I will just tell you that if you do it correctly, you will get 1, 1, 1. You'll get x equals 1, y equals 1, and z equals 1. You can see that, by the way, because 7 minus 2 plus 7 is 12. 5 plus 13 minus 6 is 12. Negative 4 plus 11 plus 3 is 10. You can see that 1 comma 1 comma 1 works out, but I want you to actually work it out with Kramer's rule and be amazed that it's actually going to work. Okay, now we're going to go back. Hopefully, okay, we're good. So now we have an example of Kramer's rule. So here's 3 equations, and there's my constants, and the determinant of A is this determinant right here, which is very easy to figure out that it's 10. By the way, once you figure out the determinant of the coefficients, you can use that same number 3 times. You don't have to keep on redoing it. Anyway, let's just do the x variable. Oops. If we just do the x variable, so we replace this first, the x column, with the coefficients 1, 0, 2, and divide that by 10. Now, when we write this out, we we notice that when I make this replacement of the 1, 0, 2, I have 2 zeros now in the middle row. So we're going to use the middle row, and we just have to do 1 times negative 1 to the 5th power, which is negative 1, times the determinant of 1, 2, 2, negative 4, which is what's left, and that just becomes 4, and then 4, and dividing it by that becomes 8. This becomes 8 divided by 10, which is all we're doing. You can find the y and the z. By the way, once I know that x is 4/5, I could take this middle equation and very easily see that z is negative 8/5, and then I could take that and back substitute and get y. So that's not a problem. Although I would like you to actually work them out with Kramer's rule to see if you get those answers. Just like in that other problem, I wanted to see that you get the answers 1 to 1. But this is Kramer's rule, and it works, and it's amazing. It's awesome. Awesome. What I love about this is that normally when you solve a system of equations, you got to start thinking, I'm going to do this and eliminate this and substitute that and blah, blah. Here, Kramer's rule just gives you a way you can just do it without having to think. It's kind of cool. It's like just just follow the steps and pow, you get your answer. It's kind of cool. Even though I love thinking, but I think it's kind of cool that you can have a formula like quadratic formula. You don't just start thinking about factoring what you do. You just plug in the quadratic formula to get your answer. Anyway, now that's it for Kramer's rule. And the next thing we're going to do is to use determinants. This is the last part of this section that we're about to embark on. Is to use determinants to find the area of a triangle in the plane. How do you like that? In the XY plane. So here we are in the XY plane, and we have a triangle, and the points of the triangle are x1, y1, x2, y2, x3, y3, and the area, believe it or not, is I take my points x1, y1, x2, y2, x3, y3, and then just line them up like that. For this third column, I fill in ones. Now we have a square matrix. So if I take the determinant of this matrix, 1/2 of this determinant, that gives me the area. Now, the reason it says plus or minus 1/2 is because when you do a determinant, you might get a positive number, you might get a negative number. So if you get a negative number, multiply it by the 1/2 to make it positive. If you get a positive number, multiply it by the positive to keep it positive. Now, I'm not going to go through the whole proof in painstaking format. I'll just show you the gist of it. Basically, you got over here. So if you look here, there's 3 trapezoids. Well, there's more than 3, but here's 3 trapezoids. There's one trapezoid whose base is right here and goes all the way up here. So it's a tall, thin trapezoid. Then I have a second trapezoid whose base goes from x3 to x2, and it goes all the way up here. And it's a second big tall trapezoid. These 2 big tall trapezoids, they're part white, part blue. That's part white, part blue. Fine. Now there's a third trapezoid sort of lying down, and it's all white. This guy right there. So it goes from x, goes here to there to there to there. So the area of the blue triangle is equal to the area of the 2 trapezoids minus the area of the lying down trapezoid. In other words, if I add the areas of these 2 trapezoids, I get the whole thing, and then I subtract the white part down here, the lying down trapezoid. I'm going to be left with the blue triangle. Now, you can figure it out with just basic geometry. Excuse me, you can figure out with just basic geometry that you know, is 1/2 the sum of the bases times the height, and so you could just do all that to get these guys right there, and that is equal to this determinant. Now, how do you see that? I don't know. You got to crunch it. Take this determinant and work it all out. You'll see it get a whole string of variables. Take this guy, work it all out. You'll see it's the same thing. There's no elegant way to see that, but you do have an awesome formula, and let's use that formula a little bit. Okay, so as you see, to find the area of this triangle. So 0, 2, 2, 4, 3. And here we go. So we're just going to plug that in to this determinant, and pow, we are in good shape. We just the determinant of this big thing is 3. 1/2 times that. I'm sorry, it's -3. 1/2 that gives me -3/2. But again, it's an area, so we just say 3/2. By the way, the order in which you list the points will make it positive or negative, because when you switch the rows of a matrix, then it makes a determinant positive or negative. And so it doesn't really matter what order you put everything in, because if you get a positive number, great. If you get a negative number, just make it positive. But you're always going to get the same actual number. That's what I'm trying to say. It may be positive, it may be negative, but it'll always be, you'll get the right number. But wait a second. You may get a positive number, you may get a negative number, but what happens if you get a number that is neither positive nor negative? Well, there's only one number I know of like that, and that's the number 0. What happens if you take this and you get a 0 for your determinant? Well, what does that mean? I mean, we're not talking about whether a matrix is a vertical. Well, what happens if you get a 0 determinant? What does that mean? Well, that if the area of the triangle is 0, that must mean that the triangle is squished down to just be a straight line. So, gentlemen and ladies, we now have a formula, or a test, I should say, for collinearity of points in a plane. If you take this matrix, like we've been discussing, if you take the matrix that we've been talking about and you get a value of 0, that tells it that the 3 points are collinear. And here's an example. We have these 3 points, 0, 1, 2, 2, 4, 3. You crunch out the determinant, you get 0. That tells me that these points, Now, of course, I can see the collinear because I'm looking at a picture of it. But what if there's no picture? First, by the way, looking at pictures is a bad idea in geometry because that could be an angle. That could be an angle of 179. Suppose that was 179.9 degrees. It would look like a straight line, to your eye. So don't judge too much based on pictures. It's always good to verify things algebraically, but you can see because you get a determinant of 0, that means these must be in a straight line, and that's the formula right down here. That's the test for collinearity of points in the xy plane. But wait a second. Suppose I would have in this oh darn. Suppose I had in this formula, I have my x1, y1, that's a random point, x2, y2, that's a random point. And on the bottom row, instead of having x3, y3, I just have a plane x and a plane y. Now, what's the difference? x3, y3 are constants. That's just the third point. But what if I, instead of having a constant, I put the variable x, the variable y? Well, if you think about it, this would wind up being all the xy points, which yield a 0 determinant with the first and second point, which really means it's all the points on the plane that are collinear with those 2 points, which means, drum roll please, we have the equation. In other words, now notice here they put the xy on top. Doesn't matter because like I say, switching rows around just makes the determinant positive or negative, but we're dealing with 0, so it doesn't matter positive or negative. But the point is that this, believe it or not, is the formula, is an equation now for a straight line. It's a line that goes to these 2 points, y1 and x2, y2. Because this is all the xy points on the plane, which will make this determinant equal 0, which of course we know is a straight line. And let's do an example. So we have 2, 4 and -1, 3. So what we want to do here is set up our determinant. So we have here's our 2, 4. That's our -1, 3. That's our xy. As usual, the third column is all just 1s, and we set this guy equal to 0, and we evaluate it, and we get, drum roll please again, we get x minus 3y equals -10 after we simplify everything. Because again, this is just a constant times x, that's a constant times y, that's just another constant. Bring everything over appropriately, and pow, we are in business. So we have so this here, even though it doesn't look like it, this is the equation. This equation here is the same as that bottom equation down there, that guy right there. So that's fabulous. That is fabulous and amazing. But I know what you're thinking. You're thinking, hey, this is 2 dimensions. What about 3 dimensions? Well, guess what? We could do the same basic sort of similar formula. They're calling it here a generalization. Works for the volume of a tetrahedron. So if I have 4 points in space, that creates what's called a tetrahedron. And here we have a formula for the volume. It's the same type of formula that we had for a triangle in the plane, but instead of multiplying by a half, we're multiplying by 1/6. But this is my first point, my second point, my third point, my fourth point. Pow, it's all there. And let's so here's a tetrahedron. That's what it looks like. And these are the vertices. And we want to find the volume of this tetrahedron. Well, easy peasy lemon squeezy. We're just going to use the formula that we just learned a second ago. And we're going to say, here's the 4 points. That's the first point, second point. That last column was all 1s. We're going to multiply it by 6. We get -72 times 1/6, which is -12. And of course, we're just going to make it +12. Now, similarly, if the 4 points, if I get a 0 determinant, that means the 4 points, that means the tetrahedron is squashed down, meaning that all 4 points lie on the same plane, or in other words, are coplanar. So this is a test now for pointing coplanar in space. If the determinant equals 0, then these 4 points are coplanar. I mean, they all lie in the same plane. By the way, any 2 points lie in a straight line. So there's no such thing as collinearity of just 2 points. Any 3 points lie in the same plane. So there's no such thing as 3 points being coplanar, because 3 points are always coplanar. But it's when you have that 4th point, for coplanarness, or the 3rd point for collinearity. Anyway, and similarly, doing the exact same logic as before, we also have the 3-point form of the equation of a plane. Because in other words, that's my first point, there's my second point, that's my third point, and on top I just have the regular variables x, y, z, and this last column is all ones like before, and I set it equal to 0. So same, really, it's analogous, to what we did in with a triangle in the plane. So here we have 3 points, 1, 2, 3, and we know that 3 points determine a plane. What is the equation of that plane? Well, we're going to use this here to find that equation. If any of you have ever taken Calc 3, I don't know if they do this in Calc 3, this particular method, but it's pretty awesome. Anyway, so we're lining everything up. We're putting in our 3 points. We're putting the x, y, z on top. Now we have to take the determinants. Usually, it doesn't really, technically, it doesn't matter, but usually when we do the determinants, we go across the row with the variables in it. Not that you have to do it that way. That's pretty typical. And here we go. Let's see. We're gonna start though. We're gonna start the fun by subtracting the 4th column from the 2nd column. See, if I take this 4th column and I subtract it from here, I wind up getting a whole nice row of zeros, except for one at the end. You don't want all zeros, because then it's automatically 0. We want something where x, y, and z. Anyway, so now I can expand it. I'm going to expand it across the 2nd row, which is a very cool thing to do. And I get this sucker right here. X times this determinant minus, notice that became y minus 1. When I did the subtraction, what had been a y became y minus 1. Times this determinant plus z times that determinant equals 0. Crunch everything, put everything together, gather up all your terms, blah, 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 and you wind up with the equation 4x minus 3y plus 5z equals -3. And that's a very cool, straightforward way of finding the equation of a plane that goes to 3 points. I want to mention as a side point, or just what the book says, that Kepler's first law of planetary motion is that planets orbit an ellipse. Generally ellipse, you have ax squared bxy c y squared dx ey, and of course you have the f. Usually we put the f on the other side, but it doesn't matter. Anyway, so it turns out that there's a very similar process to find the equation of ellipse. So it turns out if you have if you have 5 points, if you have a planet orbiting, and the coordinates of 5 points, you could use those 5 points, stick those 5 points, point 1, point 2, point 3, point 4, and then point 5. You could stick those 5 points into this, and then put your general x squared, xy, y squared, x, and y, and then across the column of ones. So you can use this determinant here to find the equation of the planet, which is awesomely cool. And that, my friends, is the end of our of section 3.4 applications. And it has been a privilege and a pleasure sharing this with you.